They said it was simply another comet. They were wrong. Something came into our solar system on the 1st of July 2025, and it shattered every rule of physics we know. It was going 130,000 miles per hour. The tail was pointing the opposite way. Then quantum AI looked at its structure, and scientists stopped talking. What they found wasn't rock or ice. It was made, constructed, made. It hid below the sun for weeks, and as NASA followed its next move, they concluded we might not be alone anymore. You'll be scared by what happened over those secret weeks. The Atlas survey team, which keeps an eye on objects near Earth and tracks celestial bodies, was looking at readings that seemed completely wrong. Because what they were seeing didn't make sense according to recognized astronomical concepts, their first thought was to check their equipment for problems. This wasn't just another asteroid floating through space, or an ordinary comet passing through our area. The object, which would later be called 3I, Atlas, was moving with such accuracy that even seasoned astronomers had to stop and redo their observations several times. The path wasn't following the regular patterns that natural space objects like to follow. There was something planned about its journey, something that made it seem like it was moving through the blackness between stars for a reason. NASA's communication teams were attempting to figure out exactly what their instruments were telling them just a few hours after the first discovery. The name 3I, Atlas, made this the third confirmed interstellar object in all of human history. The last two visits from outside our solar system, Oumuamua in 2017 and Comet Borisov in 2019, had already created a lot of interest and debate among scientists. But this new item was doing something that neither of those things had done before. It was doing things that went against the basic norms of physics as we know them now. The first measurements of the object's speed showed that it had an orbital eccentricity of more than 6, which broke all prior records for interstellar objects transiting through our solar system. Most comets and asteroids, on the other hand, follow predictable elliptical or parabolic courses that can be estimated with a fair amount of precision after a lot of observations have been made. Astronomers can model and predict their paths because gravity and momentum control their movements. But 3I, Atlas, was moving across space in a way that was so straight and accurate that it looked like it knew exactly where it was going. The arithmetic was correct, but it told a story that sounded unbelievable. It wasn't just the speed or the strange path that got everyone's attention. What occurred was that telescopes in different parts of the Earth began sending back detailed pictures. All of the observatories who pointed their instruments at this strange visitor saw the same thing, which is something that shouldn't happen according to our existing models of how comets behave. Instead of a comet tail that streams away from the sun, driven by solar radiation pressure, like cosmic hair blown back by an unseen wind, 3I, Atlas was doing the reverse. Things were being thrown right at the sun. This wasn't a small technical element that only experts would find in study publications. This finding was so big that it made experienced astronomers doubt decades of what they thought they knew about how celestial bodies move. The people working on the Atlas survey started right once, comparing what they saw with data from the past. They looked up pictures of every comet that had ever been seen, ran their measurements through every known computer model, and got in touch with colleagues at schools all across the world. They couldn't find anything in the database that matched what they were seeing. There had never been a pattern like this before. The dust and gas flowing off the object looked like they were too heavy to be moved by solar wind or radiation pressure alone. But it was evident that it was being pushed out of the side of the nucleus that faced the sun with a lot of force. Within a few days after the discovery, several observatories had confirmed it. The Lowell Discovery Telescope in Arizona and the Gemini South Telescope in Chile both said they saw the same thing. There was a bright, steady plume aiming straight toward the sun in every frame they took across several observation periods. The pictures depicted something that went outside the laws of physics. When comets get close to the sun, the radiation from the sun heats up their icy surfaces, causing the material to sublimate and create the tails that we usually see with these objects. The solar wind, which is a steady stream of charged particles moving away from the sun, pushes this material away from the sun and makes tails that can go for millions of miles. This procedure is so reliable and well known that it is used to teach basic astronomy. This is the pattern that every comet that has been seen by people has followed. Up until now, imagine trying to toss a baseball directly into the wind on a really windy day. The ball should be pushed back, or at least slowed down a lot, not sped up even more. That's pretty much what solar radiation does to the gas and dust in comets. The sun is like a giant cosmic hairdryer that blows particles off its surface at extraordinary speeds all the time. The pressure from sunlight is strong enough to change the shape of comet tails and potentially power speculative spacecraft known as solar sails. This force can be measured, predicted, and has never been seen to fail. But 3I, Atlas, was following a whole separate set of regulations. The Hubble Space Telescope's high-resolution images gave us even more comprehensive views of the anomaly. The plume wasn't following the item as it went through space, which is what would happen with a normal comet. Instead, material was moving away from the sunlit side of the nucleus and toward the sun. Astronomers carefully tracked its position over several days and found that it always pointed west in the sky, which was the same as pointing toward the sun in three-dimensional space. The feature kept its shape and direction after many observation periods. This wasn't just a strange thing that showed up in one picture and then disappeared in the next. This wasn't a mistake in the measurement or a flaw in the way the telescope worked. This was a bright, persistent feature that kept showing up and wouldn't act like something natural should. Different teams using different tools in different places all saw the same thing, which ruled out the chance of equipment failure or mistakes in the process. Solar radiation pressure is one of the most well-known and reliable forces in space. It's what makes the pretty shows we see when comets come into the inner solar system. Engineers utilize this information while planning missions that use solar sails to move. Many times, scientists have tested and confirmed the algebra that explains how light pushes on particles. Those particles would need to be launched with enough force to resist the continual wind in space in order for the material to flow toward the sun instead of away from it. The only way to get such a result would be to use some form of focused propulsion system that could fight against the natural physics of light pressure. Scientists tried every way they could to fit the observations into models that were already known. Computer simulations ran for days, changing things like particle size, solar wind strength, magnetic field arrangement, and every other natural explanation that could be thought of. Teams worked all day and night to test their ideas. It's possible that the particles were charged in a way that was out of the ordinary, which caused them to react differently to the solar magnetic field. There may have been an unusual sublimation process happening that had never been seen before. It's possible that the measurements were being read wrong because of the angle of observation. Nothing worked. None of the models that tried to explain the sunward plume using natural processes were able to match what was seen. The dust seemed way too big to be pushed back by solar wind, but it was being thrown out with too much force to just fall toward the sun because of gravity. It looked like the scenario went against the basic rules of cause and effect. When the James Webb Space Telescope pointed its advanced equipment at 3I Atlas in early August 2025, the chemical analysis that came back left scientists speechless as they stared at their displays. The spectroscopic results showed a composition that didn't fit with any known way that natural comets develop. This object was mostly made of carbon dioxide, not water ice like most comets that come from our solar system. The levels of concentration were so high that they were absolutely outside of what had ever been seen previously. The test showed that there was around 8 times as much carbon dioxide as water. We need to look at what is normal for comets to see how amazing this discovery is. The ratio of carbon dioxide to water in most of the comets in our solar system is between 0.1 and 0.12. These are the normal amounts found in comets from the Kuiper Belt, which lies beyond Neptune's orbit, and the Oort cloud, which is a faraway place where frozen bodies are stored. Astronomers sometimes find very unusual specimens that could have ratios as high as 4. These are already thought to be severe outliers that need more attention and research. The figure for 3I Atlas was 4 standard deviations higher than the typical trend for all known solar system comets. This puts it in a statistical group that is so unusual that just one other comet in the entire history of astronomy has ever had readings that were even close to this. The Webb telescope team utilized their best spectrographic tools to look at the light that was coming through the coma, which is the cloud of gas and dust around the nucleus. At certain wavelengths, the carbon dioxide signal entirely drowned out the water signature, making it impossible to make any mistakes or misunderstand the data. But the strange carbon dioxide levels weren't the only chemical surprises. The Very Large Telescope Array in Chile, which is one of the most powerful ground-based observing facilities on Earth, found something even stranger in the spectrum analysis. The stuff that was coming out of the item had atomic nickel in it. It's not completely unheard of to detect metals in comets. A lot of comets have little amounts of different elements in them. When they reach close enough to the sun, these elements can get hot enough to give off light at certain wavelengths. But what made this discovery so important was what wasn't found with the nickel. The spectral results clearly showed that iron was not present. This is a big difficulty for any explanation of natural formation since nickel and iron are made together in stellar nucleosynthesis, which is the process by which elements are made in the hearts of stars. When huge stars burst as supernovae, they send these elements into space, where they eventually become part of new planetary systems, asteroids, and comets. Nickel and iron always show up together in the same amounts in every natural cosmic setting we've looked at. This is because they are made through the same nuclear processes and have comparable chemical properties. Nickel without iron strongly suggested that these components had been separated by some form of refining process. In industrial metallurgy on Earth, many methods are used to make nickel alloys that have little or no iron in them. These processes need controlled settings, certain temperatures and pressures, and careful chemical steps. Nature doesn't make them happen on its own. The spectroscopic signature from 3I, Atlas, showed signs of manufactured components, not the raw cosmic debris that makes up natural comets. A number of study groups started working on their own to confirm these results and look into what they might mean. Astronomers, astrophysicists, and planetary scientists from all across the world shared the data. Everyone who looked at the spectrum analysis came to the same conclusion. The chemical makeup didn't match any of the current theories about how things form in the frigid, faraway areas between stars. Comets are basically dirty snowballs that have been around for billions of years and haven't changed much since the early solar system. The components that make them up come from the protoplanetary disk that they formed from. They shouldn't look like they were made in a factory. More examinations showed other strange chemical properties that made the enigma even deeper. The stuff coming out of 3I, Atlas, had very consistent properties throughout time. As they rotate, different parts of a natural comet's surface are exposed to sunlight, which causes the comet to outgas in different ways. The makeup of the stuff that comes off a comet can alter a lot depending on which section of the nucleus is facing the sun at the time. This is because different parts of the nucleus frequently have varied amounts of different ices and embedded elements. But 3I, Atlas's spectral signals were very consistent, which made us think that its structure was more uniform than what we'd expect from a real body. The isotope ratios found in the carbon dioxide also made people wonder. Isotopes are distinct forms of elements that have variable numbers of neutrons in their atomic nuclei. We can learn a lot about where and how materials formed by looking at the relative amounts of different isotopes. Things from our solar system have unique isotopic fingerprints that show what the solar nebula was like 4.5 billion years ago. 3I, Atlas was clearly from outside our solar system, which would explain some of the differences in isotopes. However, some of the ratios seem strange, even when you take into account that it formed in a completely different stellar environment. The object's thermal qualities added another dimension to the mystery. Astronomers kept a close eye on how 3I, Atlas's brightness varied and how its outgassing rate altered as it got closer to the sun and got more solar energy. Natural comets follow thermal models that are easy to anticipate. We can figure out how much sunlight strikes their surface, how much of that energy goes into heating the nucleus instead of bouncing back into space, and how the rate of sublimation should go up as the temperature goes up. The way 3I, Atlas, acted didn't really fit these models either. The thing seemed like it was taking in and controlling heat in ways that made it seem like it had a more complicated interior structure than just a ball of ice and dust. Some parts seemed to let heat through better than others. The rate of outgassing growth with solar heating didn't follow the smooth curve that typical comet models said it would. Instead, the activity displayed patterns that could be explained by internal compartmentalization or layered structures with varied thermal characteristics. Spectroscopic investigation also found small levels of other strange substances in the coma. The first reports focused on the carbon dioxide and nickel, but a closer look showed modest amounts of components that didn't seem to belong in a natural comet environment. Some of these compounds are usually linked to processes that happen at high temperatures, yet they were mixed with materials that definitely developed in the very cold of interstellar space. This combination indicated either an exceptionally atypical creation history or the potential that various components of the object originated from distinct sources. When looked at with polarimetry, a method that looks at how light is scattered by particles, the dust particles that were thrown out with the gas also displayed fascinating features. The polarization patterns showed that the dust grains had sizes and shapes that were rather homogeneous, which is not what you would expect from normal cometary dust. Comet dust usually has a wide range of particle sizes and shapes that aren't normal. This is because of the random ways they formed and the mechanical weathering they've gone through over billions of years. The dust from 3I, Atlas, looked more homogeneous, like it had been made or treated to have particular qualities. Each of these chemical and physical features may have valid natural explanations, even if those explanations needed some uncommon circumstances or rare formation conditions. But, when you put them all together, they made a picture that was harder and harder to fit with any known natural formation scenario. The combination of very high levels of carbon dioxide, processed nickel without iron, strange thermal management, consistent spectrum signatures, and uniform dust qualities made a chemical fingerprint that is not like anything we have seen in comets, asteroids, or any other natural solar system body. Research groups started sharing their early studies in astronomy journals and at conferences. The papers were well written and focused on observations and measurements instead than making assumptions. Scientists are naturally wary of making remarkable assertions, particularly when such assertions imply answers that enter speculative domains. But the facts were clear. We expected a natural visitor from another star system to have a certain chemical makeup, but 3I, Atlas, didn't have that. Astronomers kept an eye on 3I, Atlas, as it moved through the solar system. Orbital mechanics experts started to figure out its exact path and found something that made the already strange scenario even more interesting. The way this thing there was moving was strange not only in terms of speed and direction, it was moving through our solar system in a way that would put it quite near to 3 main planets in a very short amount of time. It felt like these interactions were planned out because the distances and times were so carefully planned. The trajectory study suggested that 3I, Atlas, would be able to see Jupiter, Saturn, and Uranus as it traveled through our part of the solar system. It was especially surprising that these weren't just random flybys at random distances. The distance between each meeting would be just right for gravitational interactions and scientific observation. The closest approach to Jupiter would be at a distance where the planet's huge gravitational field would have a big effect on the object's speed and orientation. If the object had any form of sensor equipment, it may have analyzed Saturn's rings and magnetic field in detail at the point when it met the planet. The Uranus pass would happen at a distance that was perfect for looking at that planet's strange slanted magnetic field. It took some advanced statistical analysis to figure out how likely it was that such a trajectory would happen on its own. Orbital dynamics specialists from multiple institutions conducted thousands of computer simulations to produce random interstellar routes and assess how many would inherently lead to such an exact sequence of planetary encounters. The results were really interesting. It was quite unlikely that an object would come into our solar system from a random direction and organically follow a route that would take it past 3 main planets at such specified distances. The calculations showed that the chances of such a random alignment happening were about 1 in several million. The orbit's eccentricity value was another piece of information that didn't seem to fit with what was logical. Orbital eccentricity tells us how far an orbit is from being a complete circle. A value of 0 means a circular orbit, values between 0 and 1 mean elliptical orbits, and values more than 1 mean hyperbolic trajectories, which means that the object isn't held by the sun's gravity and will eventually depart the solar system. The eccentricity of 3I, Atlas, was about 6.141, which was a new record for debris from other stars transiting through our system. To get a better idea of what this number signifies, think about how most interplanetary visitors have eccentricities that are just a little over 1, maybe between 1.1 and 1.5. These numbers show hyperbolic routes that bend a lot when the item swings through the inner solar system because of the sun's gravity. But an eccentricity of 6.141 means that the course was so straight and quick that the sun's gravity hardly changed it at all. It was like watching a bullet go past without changing course or speed. This very high figure showed that 3I, Atlas, was moving so fast that even our sun, which has a very strong gravitational attraction, could barely change its path. The trajectory's retrograde motion was another strange thing about it. Most things in our solar system go around the sun in the same direction. This is because of the angular momentum that was present in the gas and dust cloud that produced the solar system. When objects from other galaxies pass through, they usually keep at least some of the general rotation of the Milky Way's matter. But 3I, Atlas, was going the wrong way compared to the regular flow of cosmic debris. It was going the opposite way of how stars and debris usually move in our galactic neighborhood. This backward course made it seem like it would have taken a lot of energy to speed up the object against the normal flow of galactic rotation. If a star system randomly ejects anything through gravitational interactions, it usually moves at speeds that keep at least portion of the original orbital motion. To fully change direction and get the speed needed to reach our solar system while heading backward, we would need more than just the gravitational slingshot effects of planetary contacts in its home system. The energy needs suggested some kind of active propulsion instead of passive gravity acceleration. As scientists tried to figure out these strange orbits, new kinds of analysis became available because to developments in quantum computing and artificial intelligence. A number of academic organizations had created quantum-enhanced AI systems that were specifically made to look at astronomical data in ways that had never been done before. These systems could look at spectroscopic information, thermal signatures, and structural data in ways that showed patterns that other methods of analysis couldn't see. When these advanced technologies were pointed at the data coming in from 3I, Atlas, they found something amazing. The AI analysis showed what looked like a layered structure with different areas that had varying material qualities. This wasn't the homogeneous or random collection of pieces that you would anticipate from a natural piece of debris. The thing, on the other hand, seemed like it had well-defined pieces, as if distinct parts had been made for different jobs. The outer layers have properties that were similar to those of materials used to shield spaceships from dramatic temperature changes and keep things safe from the harsh environment of interstellar space. A further in-depth look at the structure showed that there were parts that may be called propulsion-related. The quantum systems found molecular patterns and material concentrations in some areas that looked more like advanced engine parts than natural rock or ice formations. These weren't precise copies of human technology, but the patterns of how they worked were clear. It looked like the materials were set up in a way that would make it easier to manage the release of energy and create directed thrust. The isotope ratios found in different elements throughout the structure were probably the most interesting thing. Some isotopes exhibited purification levels unattainable through natural methods. Elements in nature are made up of different isotopes mixed together in amounts that depend on nuclear physics and the conditions in which they created. To separate isotopes or add more of certain isotopic forms, you need advanced technology and carefully managed industrial operations. We use this on Earth for a lot of things, like nuclear power and medical treatments, but it needs specific facilities and a lot of energy. The isotopic signatures from 3I Atlas indicated that comparable refinement methods had been utilized on at least a portion of its constituent materials. The quantum AI systems also found what seemed like modular building methods. Different parts of the item had different material signatures, density fluctuations, and structural properties. This made it look like different parts were made individually and then put together to make the final shape. Natural bodies, on the other hand, originate by accretion and collision, which leads to compositions that are mostly the same or at least random distributions of components. The modularity found in 3I Atlas pointed to planned assembly and methodical engineering. It seems that the building also had a way to control the temperature. As the item got closer to the sun and the solar heating got stronger, thermal monitoring showed that different areas reacted differently to the radiation coming in. It looked like some places were made to soak up and spread heat well, while others looked like they were protected from variations in temperature. This level of advanced thermal control doesn't just happen by chance. When the sun gets close to natural objects, they can get thermal stress, which can cause them to crack, blow out gas, and modify their structure. But it looked like 3I Atlas was handling the heat load in a regulated way. The quantum analysis also found what scientists started calling information storage signatures. Some of the chemicals in the structure have molecular arrangements that could keep very stable structures for long periods of time. These materials had the kind of accuracy and long-term stability that would be perfect for keeping data safe on trips that last thousands or even millions of years. The molecular architectures weren't just random. They indicated patterns that were in line with organized information architecture, but the exact content was still too hard for us to figure out. The research also showed that radiation resistance was a feature that came up. Cosmic rays and high-energy particles fill interstellar space, and over time they break down stuff. For long-term space missions, it's important to choose materials and shields carefully so that equipment doesn't break and structures don't get damaged. 3I Atlas was made up of materials that were known to be resistant to radiation and could keep their shape even after being exposed to the harsh radiation environment between stars for a long time. This wasn't a lucky coincidence in the way the pieces fit together. It looked like these materials were chosen because they were good at protecting things. The structural parts of the thing have design features that made it possible to keep its shape even when the temperature changed a lot. Interstellar space is almost completely empty, whereas getting close to stars can make things hot enough to turn them into gas. It is not common to find materials that can withstand this whole range without breaking, warping, or breaking down. These materials need careful engineering. The quantum systems found material choices and structural arrangements that seemed like they were carefully planned to deal with these extremes. All of these data pointed to manufacturing procedures and material science that were much beyond what people can do now, maybe by hundreds or even thousands of years. But these technologies didn't seem to break any known laws of physics or work on fundamentally different principles. The quantum AI systems could see the functional patterns because they were based on the same physical rules that govern the construction of human spaceships, but they were used with far more accuracy, complexity, and progress. This was engineering that we could understand, but it was taken to an extreme level. It wasn't foreign technology that we couldn't grasp. 3 years later, in October 2025, 3I Atlas reached a very important stage in its voyage through our solar system. The object went behind the sun, which astronomers call solar conjunction. During this time, there was a full blackout of observations since the sun's strong radiation and brightness made it impossible for any telescope on Earth to keep track. For weeks, this enigmatic visitor would be hidden from people during what could be the most essential part of its whole journey through our solar system. From an orbital mechanics point of view, the timing of this blackout couldn't have been more important. Perihelion is the point at which an object comes closest to the sun. This is also the point at which any spacecraft has the most kinetic energy. This is also the point where any propulsive maneuver would have the biggest effect on the path that follows. Because of the Oberth effect, mission planners at space agencies all around the world often plan important engine burns to happen at perihelion. This idea of orbital mechanics lets spacecraft increase the power of their push by firing at the point of highest speed. A modest engine igniting at perihelion can affect the path of an object in space in a way that would need a lot more fuel if it happened at any other point in the orbit. For 3I Atlas, which has a history of strange acceleration and that strange plume going toward the sun, this conjunction period was the best time for any major changes to happen, without anyone noticing. The object had already been accelerating in a way that could be measured that wasn't due to gravity as it got closer. Exact measurements showed that the acceleration was always about 4 times 10 to the -7th meters per second squared, pushing continuously toward the sun, which was the same direction as that impossible plume. If this acceleration was really proof of some kind of propulsion system, and not just natural outgassing, then perihelion would be the best time and place for a big move. For several weeks, the conjunction window was open, and during that time nothing could be seen or quantified regarding how the object acted. The sun's glare was so strong that no visible light could get through it. The strong electromagnetic radiation coming from the solar plasma entirely drowned out radio signals that could ordinarily be used to track spacecraft or learn more about them. The sun's huge presence was too much for even the most sensitive sensors that could detect gravity. It made a complete data gap at the exact time when the most important things might have been happening. It was like having a security camera system go black right before the most crucial thing happened. Planetary defense teams in different places throughout the world had marked this time as a critical watch period, although everyone knew that there was nothing they could truly watch during this time. The automated alarm systems were meticulously set up and ready to start scanning as soon as 3I Atlas came out from behind the sun. These systems would be checking for any changes in the path, brightness, or spectral features, or any other signs that something important had happened during those weeks when they were hidden. The lack of observation caused both major technical problems and a lot of discussion in the scientific community about what might have been going on during the blackout time. At the Jet Propulsion Laboratory in California, the mission planners had previously done a lot of math that showed that even little changes in speed at perihelion might have a big effect on the object's course through the outer solar system. A change in trajectory of only a few meters per second, which wouldn't have much of an effect on propulsion needs, might move the spacecraft millions of kilometers closer to or farther away from the outer planets. This kind of move could create brand new chances to see things that weren't on the initial expected path. Or, it may send the item on a path that was radically different from what had been predicted based on the pre-conjunction orbit, causing it to disappear into deep space. There was a lot of uncertainty, and all anyone could do was wait for the object to show up again and see what had changed, if anything. Weeks before the conjunction, ground-based observatories started getting ready for their observing operations. Facilities all across the world set aside telescope time, so that several separate instruments would be ready to collect data as soon as 3I Atlas became visible again. Protocols were put in place so that universities could immediately share data with one another. This way, any important discoveries could be checked and studied as soon as possible. The astronomical community was gathering resources on a level that is not often seen, except during big events, like supernovae or comet strikes. They were also putting space-based telescopes in the best places to see things. The Hubble Space Telescope had time set up for taking detailed pictures. The James Webb Space Telescope would be ready to do follow-up spectroscopic research to check if the chemical signals had changed in any manner. Other orbital observatories were getting ready to add their own special skills to what was becoming a coordinated international effort to learn more about this object. There was also the question of what the object might be doing during this hidden time besides just changing its path. If 3I Atlas was indeed some kind of probe or spaceship from another civilization, perihelion would be the perfect time to learn more about our sun. The solar atmosphere's structure, the solar magnetic field's dynamics, and the extreme radiation environment are all best examined up close. During this short time that the probe is close to our star, it would probably be built to gather as much information as possible. The weeks went by slowly for the teams that were watching for the object to show up again. Computer models kept becoming better, trying to guess where and when 3I Atlas would show up based on the trajectory before the conjunction. But everyone knew that these predictions may be entirely inaccurate if something big had happened behind the sun. The uncertainty was both frustrating and also exciting. No matter what happened next, it would either make the mystery surrounding this visitor even deeper, or provide us new information about what it is and why it is here.